Yeah, well, in the last class we derived the stress. Stress is a second order tensor. In 3D it has a 3 by 3 matrix. xg, yj, yx, gx, gy. Okay. Stress tensor has a 9 components. Okay, from sigma xx to sigma gg. And here the diagonal component give us a normal. It's named normal stress, and others are shear stress. Okay. So now we know the definition of stress. It's a concept of stress. Today, let me talk about the local equilibrium equation. Let's say we have a coordinate system x, y, g. In this coordinate system, I like to draw a cube. This is a very small cube. It has a dimension in x, dx, dy, dg. So this cube has a dimension dx, dg, dy. Okay. Here let me see only the stress in x direction. So here we have a stress sigma xx, and here we're going to have a stress sigma xx plus sigma xx dx. This is from the Taylor series expansion. Because of in this surface in the left hand side and then right hand side, there are gap. That is a dx. So, and also at the top, at the bottom, this is a stress at the bottom, stress yx, and stress at the top will be a stress yx plus partial y, partial stress yx dy. Okay, and we have two more in the front. Stress yx, and in the back let's see. So this is another yx stress. In the back we have a, let's see, xg. In the back stress xg. Okay, in the front, stress x, sorry, gx plus gx dx. Okay, this is gx. So in this cube, we have a 6 surface. In each surface, we have a 3 stress components. So total, we have 18 stresses. And for among them, 6 stresses are the in x direction. Okay? So, and then we have also, we can have this is all of these stresses will be a surface force for this cube, small cube, right? And there are going to be one more force, body force. Let's say that body force is applied to this cube. It's a Bx. This is body force. So body force has a unit, force per length cubic, force per volume. So now we have all the stresses and force about this cube. Then if I sum the force in x direction, it should be 0, right? That means equilibrium. Okay? Right? Then this is a stress and this is body force. But this is a force. So from the stress, in order to calculate the force, how can I do that? We need to multiply area, right? Because stress has a unit. Stress is defined by force per area. Okay? So then let's calculate. Let's sum the all forces acting on this small cube. Okay? So let's see the component, this one, and this one. Then this will give sigma xx plus xx dx minus sigma xx. And what's the area? dy dg. And plus, let's see this one and that one. The stress at the top and bottom. So stress yx plus yx dy minus yx. And I need to multiply area dx dg. And last one, stress yx, the gx plus gx dx minus stress gx multiply gx dx dy. And plus, we have a body force Bx, right? Bx and dx dy dg should be 0, right? If I sum everything here, it should be 0. Then let's see, we have a sigma xx here, y, this will be a disappear. Which one? Ah, G, yeah, sure. This should be G. Yes. Okay. Then we're gonna have a 3 term, and all the term has a dx, dy, dg, dx, dy, dg. So finally we're gonna have a equation we did exactly the same thing for fluid dynamics, right? Fluid mechanics. Same thing. So finally we have a equation xx plus yx plus gx plus bx equals 0. This is a local equilibrium equation in x direction. Okay. Similarly, we can derive the local equilibrium equation in y direction and z direction. So, how to derive is exactly the same. xy, yy, gy plus by equals 0. xg yg plus gg plus bg equals 0. So these are the local equilibrium equation in x and y and z direction. Okay, so and bx, by, bg are the body force. Okay, so one of very important body force is inertial force. It acts in the negative direction of the acceleration, right? So if I put that term, then we can have some equation for fluid. So for this small cube, we took the equation. Sum of the force in x direction is 0. Okay. Then let's see. Let's take the moment in this cube. Let's take the moment about y-axis m. Let's take the sum my. It should be 0, right? So we have 18 stresses on this cube, but only 4 stresses will give us a moment for that axis, right? Yeah. For example, we have a normal stress, this sigma yy. That doesn't give any moment, right? because the moment arm is 0. How about stress this one? How about this one? It doesn't give any moment. So X, Y, G. The stresses which can give us the moment is only 4. Let's say this is Y, G, Y, and G, X. That is the stress sigma GX plus GX dg. Okay, and sigma xg plus xg dx. So only these 4 stresses will give us a moment about the y-axis, right? Then let's take the moment. Let's calculate the moment. How about the body force? Body force doesn't give any moment, right? Look at this one. How can I calculate moment? Moment can be calculated by force multiplied by the moment arm, right? What's the force for that one? Force is sigma gx multiply force. I need to sorry, here y x g. I need to multiply area, this area, dx dy, right? In the back. Then what's the momentum? This is a momentum, right? This is a momentum. That is multiply dg, right? Okay, and minus sigma gx plus gx dg multiply dx dy multiply 2 dg. This is a moment by this stress, right? And also let's calculate the let's see. Okay, this is not a moment. It should be plus, right? It should be plus. Okay. Also, we're gonna have a moment, negative moment by this term and this term. Okay, and minus stress xg multiply the area dy dg multiply momentum 2 dx minus, we have a same xg multiply dy dg, sorry, plus partial xg dx multiply dy dg multiply 2 dx, right? sum should be 0, right? Sum of all these forces should be 0. And let's see. Let's see what happened here. So for all the term, we have a volume dx, dy, dg, right? So here, this is volume dx, dy, dg, and dx, dy, dg here, dx, dy, dg here. So we can get rid of that terms. Then we're gonna have finally we have a gx minus sigma xg, okay, and plus gx dg plus minus partial x xg dx equal 0, right? This is the equation we have. Here, first time I said our cube is very small, right? So it means dx and dg is very small. It will go to 0 finally. So finally we have only two terms. Sigma gx equals sigma xg. Okay? So here I just take the moment about the y. If I take the moment about x axis and g axis, I'm going to have two more equations. That is sigma xy equals sigma yx sigma yg equals sigma gy. It means our stress ij equals stress ji, or stress transpose of stress tensor is the same to stress. I mean the stress tensor is a symmetric. Okay? So from the fx equals sum fx equals 0, we derive the local equilibrium equation, and from the sum of the moment in xyg about xyg axis, we get the property of the stress tensor, which means the stress is a symmetric. This is a very important property of stress tensor. Okay? Now let me talk about stress transformation. Stress transformation. 우영아, 요즘 새가 없냐? Here let's see three axes x, y, and g, and in each three axes, let's take some point and let's draw tetrahedron. Looks like this. In each tetrahedron, this tetrahedron will have a four surface. One is in the xy plane, also one in the xg plane, one in the gy plane, and last one is a plane defined by point A, B, C. Right? So we will have a four surface. And let's see the plane surface in the plane xg. They're going to be stress gg, gy, gx. And also in the plane in YG plane, we also have a three stress component: stress xg, stress xx, stress xy. Also at the bottom, we have a stress component: stress yy, stress yg, stress yx. Okay? And also on the plane defined by point A, B, C, there are going to be some stress. So let's say some of that stress is a T, and also normal direction for this surface is a N. Let's say N. The N vector is a normal vector. N vector is normal to the surface ABC. So now I defined all the surface force acting on this tetrahedron. Okay? And also we have a four different area. For this case, if I use the sum f equals 0, okay, finally we will have a relationship. T is a vector, T1, T2, T3 equal stress xx, stress xy, stress xg, stress yx, stress yy, yg, stress gx, stress gy, stress gg, and n1, n2, n3. Here the n is a vector normal to the surface. n1, n2, n3. Okay? We can derive this one. So actual derivation is not very easy, but everybody can do that with some time. I'm going to give you just final equation. This means in somebody as a material point, if we know the stress tensor, we can calculate the stress. I mean this is a stress in for some surface. Actually, it's not a stress. It's a traction. It's named traction. Traction is a so. For example, I like to give you some example to help you understand. Okay. Let's say we are very familiar with this 1D tension problem. We're gonna have a tension in this direction and this direction. Okay. Let's say the tensioning force is P and area is A. So in this 1D body, our stress state will be a P over A. P over A. This is stress sigma XX. Let's say this is X direction, right? Then in this system, I'm gonna cut this body like that, 45 degree. Okay. The body divided by two parts, A and B. I like to see only body A, like this. So, and let's say the sigma XX is a 10. So we have a stress here, 10. Okay. And now I like to calculate the forces acting on this here using the equation we have. This is 45 degree. So in this surface, the normal vector n is a 1, 1, right? And also, for this case, our stress tensor will be a 10, 0, 0, 0, right? And let's calculate the T. T equal 10, 0, 0, 0, and 1, 2, 1, 1. This will be a 10, 0. Is that correct? So we're gonna know that we have a stress 10. Here we have a stress in this direction. This traction T doesn't have any component in Y. This is a root 10, 10. So I mean to make the part of the body A in equilibrium, we need to have this force along this cutting plane. Okay? Just think about it. Do you think this is in equilibrium or not? Just take the sum of the force. Force will be calculated by the 10 multiply A, right? How about the area of this? A root 2, right? So, if you multiply, here we have a force 10A, here we have a force 10A, right? So, this part of the body A is in equilibrium. So if we use that equation, this equation, we can calculate the traction in some internal surface and external surface. Okay? So this stress is a very basic concept to understand all the stuff in solid mechanics. Now let me talk about fundamental of strain. Okay. Let's think we have a coordinate system x, y, z. And we have an original body like that. This is your original body. Original body. And when this original body for some force, when some forces act on this body will deformed, right? This body will deformed somehow, right? This is let's say deformed body. Deformed body. Okay. And let's think, in this body there are 2 points, A and B. Okay? Both 2 points are very close. Very close. Let's say this is 2 points and this point is very close. So in x direction and so in x direction delta x, in y direction its distance is delta y. In g direction we have also distance dg. Okay? After deformation, this body 2 points will move somehow, right? These 2 points will move. Let's say this is A dash, let's say this is B dash. The point A and B will move after deformation. And before the deformation, the position of x, A is x0, y0, g0. And position for B is x0 plus delta x, y0 plus delta x, g0 plus delta g. We can think like that, right? And after deformation, A slash is x0 plus u, y0 plus v, g0 plus w. Let's say the displacement, the A point in x direction is u, displacement of A point in y direction is v, and w is displacement in g direction of the point A. Okay? Everything clear, right? Then let's say the B slash. It was a point originally delta 0 plus delta x. Okay? And it will move u plus delta u. Okay? This is additional displacement delta u about the point A. Okay? And in y direction, y0 plus delta y plus v plus delta v. In g direction, g0 plus delta g plus w plus delta w. Now let me measure the distance between A point and B point. So, and length, original length in x direction. What's the original length? Is can be calculated by the x position, x coordinates minus of A, B point minus x coordinate of A. So the original length in x direction is delta x, right? And deformed length. What's the deformed length in x direction? Can be calculated by the difference between this value and this one. Okay? It will be a delta x plus delta u. Then let's say, now let me define the strain in x direction. Strain xx is a limit delta x go to 0 and deformed length minus original length over original is this will be a delta x, delta u, limit delta x 0. This will be a partial u, partial x. So strain xx means the change of the length of very small the distance or small vector in x direction. Okay? Similarly, we can calculate we can define the strain yy, y, b, gg, g, W. So strain XX, YY, GG is a length change in X, Y, G direction. And this strain XX, YY, GG is called the normal strain. Normal strain, okay? Okay, so I like to finish all the fundamentals in solid mechanics today, and next day, next week, I like to introduce some beam theory. So we derive the normal strain, okay? So just I showed you the concept of normal strain very simply. Actually, the real strain theory is much more difficult and hard to derive, but the point of my class is just to give you concept. Again, let's consider two dimensions in X and Y plane. And this is the original body, and this is deformed body. In original body, we have a 3-point A, B, C. These 3 points A, B, C can define the angle normal pi over 2, 90 degree, right? We can define the angle by 3 points. And the distance between A and B is dx. Distance between A and C is dy. And after deformation, deformed, these 3 points will move B slash C slash, right? This point will move, and the angle, the original angle was 90 degree. That angle will change. Okay? Now let me measure the change in the angle defined by 3 point ABC. And A point is original position is x0, y0, and B x0 plus delta x, y0, C x0, y0 plus delta y. Okay? After deformation, the position of A, B, C will change somehow. X0 plus U, Y0 plus V. Right? A can be changed like that. And B, the position of B will change. X0 plus delta X plus U plus delta U, and Y0 plus V plus delta V. Right? And C, X0 plus U plus delta U, Y0 plus delta Y plus V plus delta V. Okay? So we can give the change of the position with this. Then let's draw A and A dash in the same origin. So this is A, B, C. I can plot this is A slash your C slash B slash. We can draw like that. I mean, I just move the deformed position into the original. Then I can see the change of angle. Let's say this is alpha and beta. Change in the angle will be alpha plus beta, right? Alpha plus beta is a change in the angle. If we assume the alpha is very small, then what's this angle alpha? Alpha will be this is dx and this amount of change. What's that? That's the difference in y direction between B and B, this one and that one, right? Okay, that will be a delta V. Because we moved this one in x direction and y direction. In x direction, we translate. So, I mean, otherwise we can move this one to here. The amount of the movement will U, and together to overlap like that. In y direction, the amount of movement should be V. And similarly, this will be a delta U, right? So, when the angle alpha and the beta is very small, this is an assumption for small strain. So, if alpha and beta is very smaller than 1, we can see alpha equal delta x, delta v, okay, beta equal delta y, delta u, right? And if I take the limit, okay, the shear strain xy is defined. Limit delta x, delta y goes to 0, and angle change. So this is a limit delta x, delta y goes to 0, alpha plus beta. This will be a partial b, partial x, plus partial y, partial u. Okay? So, we can calculate the angle change by this one, gamma xy. So, gamma xy is named engineering shear strain. engineering shear strain. And it gave us physical meaning, the angle change in the body. Okay? And strain xy, shear strain xy will be half of that value. This is just shear strain. Okay? Engineering shear strain and shear strains are different. So, in engineering, usually we are using that one. Okay? But to make a strain tensor, we need to use this one. Okay? So, finally, we can define the strain tensor. It's a matrix. Strain XX, strain YY, strain GG, strain XY, strain XG, strain YX, YG, strain GX, GY. This is named strain tensor. Strain tensor. Okay. And strain XY will be calculated by we already did. XV plus U Y. And strain YX will be if I change U and V and X and Y, we can have a strain YX. Sorry, 1/2. 1/2 and Y U plus X V 1/2. Okay, look at that. Strain XY and YG both are same, right? So here we can know that strain tensors are symmetric. So we already know stress tensors are symmetric, right? In strain tensor, we are saying this is a normal strain. Normal strain physically mean length change in the original body and deformed body, between two body. We can calculate the length change in X, Y, G direction with that normal strain component. Normal strain XX mean the length change in X direction. Strain YY mean the length change in Y. GG is length change in G direction. Then these are the shear part. Shear strains give us the angle change. Let's see the shear strain XY. Shear strain XY give us the angle change, actually half of the angle change between two vector. One is a base vector in X direction, the other is base vector in Y direction. So strain XY give us half of angle change in X-axis and Y-axis. Also, strain XG give us half of angle change of X and G axis. Okay, something like that. and strain matrix is symmetric, so this U this is a symmetric strain tensor. Okay? Here, the very, very important assumption for use of this strain tensor is that displacement is very small. Okay? So strain is also small. It named the small displacement, small strain assumption. So in that assumption, the strain defined like that is we named small strain tensor. This small strain is usually used in the engineering design. Okay? But this small strain cannot be used for large displacement and large strain. Usually for large strain problem. Okay? So, for example, we have a simple beam like that. Length is 10 meter. Okay? Length is 10 meter. It deformed. Maybe 5 centimeter. Okay? That displacement is smaller than overall length of this structure. Then we can use that kind of strain, small strain measure. But if this beam deformed, like maybe deflection at the center is 5 meter, okay, it's a quite large deformation. The meaning of the large and small deformation is very relative. It depends on the scale of the structure. Okay? So, for example, another example. Here we have a very small eraser. You have an eraser, right? It deforms, maybe it's 1 centimeter, 1 centimeter. You can make it deform like deform 5.5 centimeter. Even the absolute value of deformation is much smaller than this case, but because this one is the overall length or scale of dimension of this is very small, so this is a large deformation. Okay, so large deformation and large strain and small strain. This kind of concept depends on the scale of problem. Okay? So, finally, let me talk about material law. Material law. Okay, material law. Now we know the strain. Strain can be calculated from the displacement and U and B and W. That gives us a relationship between the strain and displacement. So we know the relation between strain and displacement, and also we know the equilibrium equation, local equilibrium equation, and also we know stress transformation, right? But now I never talked about the relation between stress and strain. Okay, so do you remember the 1D tension problem, bar problem? So let me talk about first about that, X and Y and G. In this coordinate system, we have a Q like that, and I'm going to apply stress sigma XX, stress XX, okay, in both sides. Then this cube will deform, stretch it in X direction, right? So from the experiment, we can calculate the relationship between strain XX and stress XYY. It's Young's modulus. It's named Young's modulus, right? Everybody know about this. Okay, no question. And if I stretch this one in X direction, what happened in Y and G direction? Y and G direction. There are going to be some contraction, right? So from here, stress strain XX is E stress XX, and we define the Poisson ratio mu is a ratio between the longitudinal direction and lateral strain in lateral direction, something like that. And mu is a minus XX GG, right? When the material is isotropic. If material is not isotropic, we're going to have a different Poisson ratio about the X and Y and G direction, but I'm already talking about isotropic material, right? Then we're going to have in 1D bar problem, tension problem, we're going to have a strain in Y direction minus mu XX, right? We know the strain XX already from this equation. Minus mu E stress XX. Similarly, we can calculate strain in G direction. Minus mu E XX will be a minus mu E strain GG. Okay? So for that cube, for a cube, when the stress XX, only stress XX is applied, we can calculate the strain XX, strain YY, strain GG. Right? It's very simple and everything are very clear. Now let me apply for that cube, let me apply the stress YY only. Okay? when the only stress YY applied, we can also calculate the strain YY from the Hooke's law. Okay, we have the same Young's modulus for strain YY and stress YY because material is isotropy. If material is not isotropy, this equation not hold. For example, composite material. You know that composite material. It made by matrix and fiber. Then fiber has a different direction. It's a, there are layer of fiber. So it has a different Young's modulus. It's an anisotropic material. Okay? So for composite, the Young's modulus for X, Y, and Z directional difference, Poisson ratio also different in each direction. It's a very complex material. Anyway, so when only stress YY applied, we can calculate the 3 strain component. Similarly, YY and GG. YY. Something like that. How about that? When the only stress in GG is applied, stress GG is applied. Okay? We can calculate also stress GG, GGE, XX from the Poisson ratio, the stress GG and stress YY from the Poisson ratio, E GG. Okay, so we calculate the strain XX, YY, GG when the only the stress XX, Y, GG is applied, separately applied. Then now think about it. Then what happened when the stress XX, Y, and GG applied together? What going to be a strain? Very simple, right? If I sum all the strain, that's going to be answer, right? So here, when XX, YY, GG are applied together, we are going to have a strain XX equal 1 over E, okay, sigma XX minus mu YY GG, okay, so YY minus mu XX GG strain GG 1 over E GG minus mu XX cross YY. Okay, so these 3 equations give us the relationship between normal stress strain and normal stress. Okay, normal stress and normal strain. So here left side we have a strain, right hand side we have a stress. We can change. We can write down the stress in terms of strain, right? Then sigma XX will be a 1 over mu. This is just inverse problem. Not very hard to get it. XA plus 1 minus 2 mu EB YY the same EYY plus 1 minus E mu EB stress GG same GG plus mu 1 plus minus E mu EB. Okay, we're going to have this equation here where EB is a sum of the strain XX plus YY plus EGG. Okay? And let me talk about notes. Let's assume we have a small body. It has a dimension to dx, dg, dy. Okay? And this is the original after deformation. After just normal deformation due to the normal strain, delta G will be a delta G plus delta G strain GG. I mean the length will be changed in, and delta X plus delta X strain XX. Delta Y plus delta Y YY. Okay? So volume will change. Look at this. Let's say original volume is a V0 and change the volume is VT. You can calculate the original volume and the change the volume very easily, right? And then, so if I calculate the change in the volume V0 delta V equal V0 Vt minus V0. This will be a change in the volume V0, right? This is change in the volume. Yeah, you can do it. You can calculate the change in the volume by this equation, right? You know how to calculate the volume of this cube and this curve, right? And then, if you take the limit dx, dy, dg go to 0, then you will have a ex plus ey plus eg. This is EB. And this is named volumetric strain. Okay, so this is a volumetric strain. So from the volumetric strain, you can calculate the volume change. Okay, so here the EB is a volumetric strain. So now to this point, I only talk about normal strain and normal stress only, but we have a shear strain and shear stress, right? So we can calculate the Poisson ratio and Young's modulus from the 1D tension test, right? Let's do the other experiment, shear experiment. Shear test, let's say shear test. Originally we have a body like that. Okay. X, Y, G. I'm going to apply the shear force sigma xy, and here sigma xy. Then this body will deform like that. Okay? There will be a change of angle. Let's say this is a change of angle engineering strain. So sigma xy equal g gamma xy. There are relationship between the angle change and the applied stress. Okay? This is a Hooke's law also for shear deformation. We are saying this is a shear stress. This is engineering shear strain. And this is shear modulus. Shear modulus. Okay? Similarly, we can get the other relationship about the strain YG and stress YG and stress GX. Stress GX. For isotropic material, for that three case, we have a same the G is a shear modulus. So here look at here. Shear strain and shear stress don't depend on the normal stress and strain. Okay, so they are independent from the normal component. So here I'm gonna add G gamma xy 2G xy strain YG G gamma YG 2G YG ZX 2G. This is a material law for 3D case. Okay, so this is a material law for 3D case. So for 3D case, we have a 6 independent strain and stress, 6 independent stress and 6 independent strain, because the strain tensor and stress tensor are symmetric. Actually, each tensor has 9 components, but both are symmetric, so we only have 6 independent components for strain and stress. So this is the relationship between strain and stress. So this is 3D material law. Okay, so stress is a function of a strain. Okay, we can write down in vector and matrix form like that. Also, this is 3D. How about 1D? 1D material law is just sigma E. This is the 1D material law, right? Now you know the 3D material law. So, any question?